welcome everybody. Good morning. Thank you for coming to my talk, fellow astrodynamicists. Sorry, let me go more with the title. I'm going to be talking about a method for detecting and responding to conjunctions in an autonomous formation flight, focusing on spacecraft in low Earth orbit in a binary spacecraft formation. So I'll take you a bit through motivation, why we care about this, how I derive the solutions, some implementation results, and then a summary conclusion. First of all, why are we here? Distributed space systems are a emerging and very impressive field where we have the capability to do new mission concepts and objectives that we have not been able to do before. I have the pleasure at Stanford University to work on the VISERS Formation Flying Mission, which is a collaboration between multiple universities and NASA, where we create a distributed spacecraft telescope where we have a 40-meter focal length separation between a detector and an optics spacecraft, or an optics and a lens spacecraft that'll operate in close proximity, ranging from tens of meters to hundreds of meters, 5 to 500 meters in low Earth orbit. And what we need to guarantee while this is going on is that we're operating safely and we're reaching our mission objectives. But safety is the key concept that I'm going to focus on right now. In the case that we have these lower cost spacecraft systems, they may have more likelihood or possibility to fail in power, attitude, or actuation or communications than other higher budget spacecraft. They also tend to have lower communication bandwidth with the ground and computation budget online. So this means that if a dangerous scenario is encountered in orbit, we need to be able to respond to it on board the spacecraft in a potentially very short time frame before a power loss notification becomes an actual power loss, before we lose control of our spacecraft actuation system. So what we seek to do is generate on board a passively safe escape maneuver to bring the formation into a safe configuration for a long period of time, over which the ground can then diagnose what has gone wrong and potentially bring the spacecraft back to a functioning formation. So we'll go through identifying the faults, how we can plan on board a response to them. That maneuver can be executed and can be checked for accuracy and how likely it is to result in a safe configuration, and hopefully we end up in a passively safe terminal state. This safety aspect is not a new investigation. Many people have approached the detection and the response to spacecraft formation collisions. Monte Carlo is the name of the game in terms of the best understanding of what collision risks are in 2D and 3D. However, they often require a large number of samples done on potentially expensive routines such as high fidelity state integration. This can be prohibitive to be performed on board. It can be mitigated a bit using methods like importance sampling, but it still remains a significant computational concern. To respond to problems, there are several methods, including onboard sequential convex programming approaches. These give you the ability to respond to generate trajectories on board, but again, there's a significant computational burden as well as a lack of guarantee of feasibility of a solution. You are a bit relying on a black box process. You can also have either pre-canned designed on the ground or onboard passively running in the background, ready to go safe abort maneuvers. These can lack flexibility. The more your spacecraft relative state is variable, the harder it is to design pre-canned maneuvers for them to be effective. And onboard running in the background also requires high computation cost, which may not be available. So what I'm going to introduce is a way to generate in an arbitrary time window a single impulsive escape maneuver that will bring a formation to a safe relative state. I will introduce this first in an unperturbed framework, and then I will introduce relevant perturbation effects in low Earth orbit. And I will introduce a method for investigating with onboard navigation uncertainty and dynamics uncertainty how we can guarantee that this will work in different cases. Into the methodology and how we design conjunction assessment and response. I'm going to be talking mostly in terms of the relative orbit elements. These are a parameterization of Keplerian orbital elements that give us a very nice intuitive understanding, or can be mapped very intuitively to the relative motion in the RTN frame, or local vertical, local horizontal frame, if you're familiar, of the relative motion of the spacecraft, to give us these nice and fairly stable, without significant perturbation effects, long-term elliptical motion in the RN plane and a translating ellipse in the RT plane. They also benefit from having a linear discrete time and control affine state transitions and a availability of perturbation effects as closed form STMs, which allow for the incorporation of perturbation effects over long term fairly accurately with linear processes. To do onboard conjunction assessment, we can identify likely regions of the relative position of the spacecraft, and we can identify when they overlap with the likely or with a specified keep out zone. We can do this specifically by propagating the relative state covariance in ROE space, which is a very efficient propagation, and a single integration of the absolute state of the spacecraft to get a fairly accurate estimation of the confidence interval containing likely to contain a deputy in the RN plane or the RT plane checked separately. The RT plane is very sensitive to onboard relative state uncertainty, especially in the along track direction, or due to things like relative differential drag, ballistic effects. It is a very, very unreliable way to guarantee separation, and so we focus mainly on separation in the RN plane, but RT plane can be checked as a backup. In order to generate a safe escape maneuver, I'll introduce what I'll call an auxiliary keep out zone. So this will be an area that will contain our strict keep out zone where we don't want the spacecraft to violate separation in, but it will also contain a shifted relative semi-major axis between the spacecraft, which is what causes a long track drift in the ROE dynamics. So what this will do is it'll introduce a zone that is not the only safe place for spacecraft to operate, but it will give a very clear and easy to use analytical condition, which we can design maneuvers around and solve directly in order to guarantee that spacecraft will respect the auxiliary keep out zone, and that auxiliary keep out zone will respect our strict operational keep out zone. The solutions of the equation I introduced in the last slide for the minimum separation between the RN trajectory and the keep out zone can be rearranged into a very convenient form, which ends up being a quadratic equation in an impulse velocity. So if you take an impulse at a specific arbitrary time, you can solve directly the R and the N component of a velocity impulse in RTN that will guarantee safe minimum separation to the auxiliary keep out zone, subject to the condition that you're not inside that keep out zone at the time of the maneuver. So this condition is very general and very powerful. And allows us to generate a safe escape maneuver in a variety of approach scenarios, as long as we are not already violating safety. This can be coupled with designation of the along track drift rate, which can be controlled directly with tangential velocity affecting the relative semi-major axis component, which allows us to control the rate at which spacecraft separate to allow them to safely separate over time, while giving us time to diagnose issues, and they'll maintain safe RN separation over that time window. This solution is given previously in an unperturbed dynamic state where the RN motion is static. We can incorporate the effects of perturbations using a Taylor expansion of the safe separation equation that I introduced previously around a reference trajectory. Doing a second order Taylor approximation allows us to solve in the same way a impulse with a quadratic equation of the impulsive velocity and the function of the ROE. This gives us the ability to, at a future time, which can nominally be selected to the time where the spacecraft cross each other in the along track plane, that safety at that moment is guaranteed in the RN space, allowing the spacecraft to safely pass by each other and continue along their journeys. It is fairly important to enforce the direction of the drift between the spacecraft to be the direction that the relative dynamics would naturally follow. The sign of the rate of change of the relative ballistic coefficient enforces a drift direction, which the spacecraft have to respect, or else they will hook around in space and come back to each other, which is a scenario by which time you'll likely have devolved your RN motion will not be a safe interaction. Finally, we'll introduce a success probability evaluation on that maneuver. It is expensive to solve directly a maneuver that will maximize the probability that your separation is above a certain threshold. Instead, we can use this very cheap solution, which is, again, just solving a quadratic. And we can evaluate coarsely over time how that maneuver will affect the minimum RN separation in a resulting orbit if you were to apply that maneuver. So this is done with an unscented transform through a nonlinear function that will generate the exact minimum separation given an input set of ROE to generate a cumulative density function of the minimum separations as a result of that maneuver. And we can then generate, explicitly say what the likelihood that a maneuver is to give you a safe resulting RN trajectory. Into the implementation, I will describe two scenarios in ROE space. So the first will be a close where you're 30 meters apart and the spacecraft are imminently about to collide within one orbit. Then I'll describe a far scenario where they are 500 meters apart in a long track space, but will collide within a few orbits. And I'll have two levels of relative navigation uncertainty representing a good double difference carrier phase GPS solution and a degraded solution. This is geometrically what the relative orbits will look like in the close, on top, and the far scenario. So this is a investigation of what the resulting success probability looks like for all these two combinations of cases. The top shows the close case, and the bottom shows the far case. And what we see is there are distinct regions where there are spikes in the likelihood that a maneuver will give you unsafe relative behavior. These spikes coincide with regions in the relative orbit where the RN safety is degraded. They introduce, there's a margin on either side typically in these regions, but they typically tend to bound around the regions where you are already violating safe RN motion. And you get peaks where you are unable to maneuver safely, and you get valleys where you're able to safely maneuver. So if you're using a forward-looking scheme, you can identify regions where you are able to safely maneuver based on a low probability of your post-maneuver trajectory violating the passive safety condition. For the efficacy of the maneuvers generated, I compare the individual maneuvers generated by the analytical solution with a approach generated with a sequential convex programming approach using a chance constraint to generate a comparison in runtime and in accuracy on how we are able to generate these maneuvers. And what we see is in most cases, the closed form analytical approach is able to generate maneuvers that are as safe within 0.001008% of accuracy of the SCP solution at less than 100th of the runtime. It's typically about 0.05 seconds to run the analytical solution, while it takes over 10 seconds to run the SCP solution. So for onboard implementation, this is a more feasible approach this is a feasible approach that we can use to accurately guarantee minimum separations in potential conjunction scenarios with much less computational results. Using this three-part system where you can identify conjunctions with a high accuracy propagation, respond to conjunctions using the closed form solutions, and then evaluate the effectiveness of your solution on the nearby region to see where you are able to best maneuver. You can guarantee that you can respond to contingency scenarios in this distributed spacecraft formation. I used visors as a test case for this as it was inspired by the work done for that project, but it should be generalizable to other spacecraft formations flying in low Earth orbit, near circular orbits. This solution is a fast solution, does not guarantee fuel optimality or maximize the probability, but future work can be done to incorporate this as a warm start to an optimization or a neural network approach. that might be able to have better, more fuel efficient, more higher probability of success solutions without the entire optimization backbone having to go through its processes. We could also investigate using adaptive safety margins based on navigation health to avoid causing unnecessary maneuvers in regions where you're highly uncertain of what your relative state is due to poor filter health, but not due to potential conjunction events. That is the conclusion of this presentation.